Okay, so we are going to start. Today's presenter is Adrià. He studied physics at Universidad de Barcelona in Spain. He is interested in lots of quantum technologies, but if he had to choose one, it would be quantum networks. His main goal is to be the CEO of a company specialized in quantum technologies. The authors of today's paper are, well, the main authors are Matteo Pompili and Carlo De Ledone. They are both PhD students at QTech, and the paper was done in collaboration with two groups. The research group of Stephanie Werner, which she's the professor of quantum communication, and their group is well, it's part of the QTech's quantum internet, which the goal is to build a large-scale quantum network. And the other group is the one from Ronald Hanson, which are specialized in spins in diamonds, and their goal is building a quantum computer or realizing quantum internet using those spins. So now I leave the floor to Adrià.
Thank you very much, Mark. So good afternoon. Today I'm presenting this paper, experimental demonstration of entanglement delivery using quantum network stack. But first, I want to put you in the context of the paper, and I will talk about a little bit of the so-called quantum internet. The vision of quantum internet is to provide a fundamentally new internet technology by enabling quantum communication between any 2 points on the Earth. But why do we need quantum internet? Internet is good, isn't it? Then why? One of the main reasons is that the smallest units of information in quantum networks are qubits, quantum bits, which are fundamentally different than classical bits. That are fundamentally different than classical bits because they can be in superposition of 0 and 1, they can be entangled with each other, they cannot be copied. These features make qubits well suited to achieve novel capabilities that are probably impossible using classical communication. As with any radical new technology, it's hard to predict all the future uses of a future quantum internet. But so far, some major applications have already been identified, ranging from cryptography to secure cloud quantum computing. There is still a long way to go to achieve a quantum internet, but so far, some important milestones we have passed some important milestones. For example, in 2015, Ronald Hanson group were the first to produce entanglement over the distance of 1.3 kilometers. Also, the same group in 2018, they made an on-demand quantum link. And also this year, they reported the first multi-node quantum network connecting 3 quantum processors. So now that you know a little bit about the context, let's move on. But first, and to understand what was done in the paper, we need to have an idea of how internet works. Internet is built using many different physical platforms like optical fibers, Ethernet cables, Wi-Fi signals. Application developers, like people who design Instagram, don't know and don't need to know if you are using Ethernet cable or Wi-Fi signal to open their website. This is because internet is built using a layered network stack. The application layer, which is the highest, can use the lower layers to send data independently of the platform being used. The set of communication protocols used in the internet are the TCP/IP protocols, which stands for Transport and Control and Internet Protocol, Transport and Control Protocol and Internet Protocol. So let's see what each layer does. The application layer is what the programs like your web browser interact with. So imagine I want to send this image of a cat to Mark. Okay, so the application layer will send the data and the request to the transport layer. Then the transport layer will chop the data into small packets, and where each packet will go to its destination independently. in the network layer, the small packets are labeled by its origin and destination and are sent through the network. In the link layer, well, the task of the link layer is to ensure that the data is received, and the data received is the correct one. Finally, the physical layer converts the data into electrical signals and send it via physical medium. So now we have an intuition of how internet works, but let's see a quantum version. It's the same, it has the same structure, but now the key ingredient is quantum entanglement. Because quantum entanglement, in quantum networks, information is transmitted via entanglement. So let's see each layer now. The physical layer is implemented by actual quantum hardware and physical connections such as optical fibers. And its main task is to attempt entanglement. The task of the link layer is to establish a reliable quantum link between two nodes that are directly connected. In other words, robust, meaning that an entanglement request should result in the delivery of an entangled pair. So the link layer instructs the physical layer to attempt entanglement till success. Quantum platform independent and on demand because we want the user to request and consume entanglement without having to understand what is the inner working of the underlying physical implementations. The network layer is the responsible to reduce entanglement, long distance entanglement between two nodes that are not connected directly. This can be achieved by the means of entanglement swapping, where we have node A and node B entangled, and node B and node C entangled. Then via teleportation, we can entangle node A and C. It is still very much a debate whether a transport layer is necessary or useful in quantum networks, and whether it would be analogous to the classical layer. But its job would be to provide the application layer with a qubit delivery service across the nodes of the network. And also here I just write a simple application that just send qubit 7 to a destination node. So now that we have an idea of how quantum internet should work, let's see what they did in the paper. So they experimentally demonstrate for the first time a link layer protocol for entanglement-based quantum networks. They described the service they want the link layer to offer, which are the protocols that can offer this service, which are the challenges, and how it's implemented. So let's see this. The service the link layer should offer would be the following. Higher layers should be able to specify these inputs to the link layer. An identifier of the remote node to generate entanglement with, the number of entangled pairs, the desired minimum fidelity for entangled pairs, whether to keep the entangled pair for future use, which is type K, measure it directly after creation, which is type M, or measure the local link while keeping alive the remote node for future use, which is type R. The measurement basis and the request timeout. Then the link layer will handle entanglement attempts till the desired pairs are created. When completing the process, the link layer should report the following outputs to higher layers: the result of the generation of entanglement, the measurement outcome, and the entanglement ID to uniquely identify the entangled pair. A design of a link layer protocol that can offer this service is given by the quantum entanglement generation protocol, QEGP, which is also accompanied by a quantum physical layer protocol called midpoint heralding protocol, MHP. These protocols were first introduced in this paper, And their main tasks are the following. First, the QEGP exposes an interface for its user to submit an entanglement request, where the user can specify all the inputs I mentioned in the previous slide. An agreement in the request is achieved by using a distributed queue protocol, which adds an entanglement request to a queue and ensures that both nodes schedule pending entanglement in the same order. Second is time synchronization, because we want that both nodes trigger entanglement in the same time to avoid wasting entanglement attempts. Then the QEGP relies on the MHP to maintain and distribute synchronized clock. Finally, it's important. One of the main tasks of MHP is to ensure that both nodes are servicing the same request, and this is achieved by using by sending an auxiliary message to the heralding station, and it's basically like the user will send an auxiliary message to the midpoint saying, hey, I'm servicing request 1 or request 2 or request 3. So the server will do the same. And when they attempt entanglement, they also send this message. Thus, the heralding station can verify that both nodes are servicing the same request. In the paper, they identified 3 main challenges. The first challenge is using a link local protocol, DQP, to schedule entanglement requests. This becomes challenging for larger networks because one node might be connected to more than just one peer. And one solution is using a centralized scalar entity which has a more comprehensive knowledge of the full network. The second challenge is interesting the triggering of entanglement attempt because even microsecond level differences on each side will result one out of sync entanglement attempt, which is a wasting attempt. So the solution is introducing a synchronization step which consists on waiting till both nodes are ready to attempt entanglement. So this is achieved by sending also an auxiliary classical message, but from node to node. So one node would say, hey, I'm ready to the other node, and the other node will do the same. So when both are ready, they will attempt entanglement. The third challenge is the capability of checking mismatches at the heralding station in real time. Because as I mentioned earlier, we send an auxiliary message saying, hey, this node would say, hey, I'm servicing request 1, and this will say another thing. So this is quite difficult experimentally. So one solution should be using also the synchronization step to, apart from saying, hey, I'm ready to produce entanglement, send information about which request the node is servicing. Then both nodes will check whether they are servicing the same request or not. The implementation. Here you can see the quantum network node architecture. So we'll go from the top to the bottom. In the application layer, the user's programs written in Python are processed. This information is sent to the instruction processor, which translates abstract quantum network applications into gates and operations. Then, if the instruction is to create entanglement, this information is sent to the link layer. It's worth to mention that in this work, they don't use a centralized scalar entity. Instead, they use a time division multiple access network scheduler, which allows us to divide the signal in different time slots, and they use each time being for a certain type of entanglement delivery, or entanglement generation. Also, it's worth to mention that they implemented a QGP such that always delivers the 5+ state. And they don't apply any mismatch verification because this is an easy setup. The experimental setup is only 2 nodes, and they It's only 2 nodes, and they don't expect any losses in the classical channel. Finally, the link layer will send the information to the hardware and to the hardware abstract layer, which encodes and serializes commands and outcomes, and it's the interface between the physical layer and higher layers. Finally, the physical layer will execute the commands issued by higher layers, and will handle critical time synchronization between the nodes. Here you can see that we have different electrical components. The most important are the DIO, which performs a real-time synchronization for entanglement generation, and the AWG, which enables real-time control of the quantum device. Here is you can see the sequence diagram, which exemplifies the general flow of the entanglement generation. So here we can see that the instruction processor issues an instruction to create entanglement to the link layer of the client. Then the link layer of the client forwards this instruction to the link layer of the server. So then both wait till the time being of the TDMA starts, and they attempt entanglement. Here we see that the first attempt ends in failure, but then they are able to generate to produce the psi plus state. But as I mentioned before, we want to deliver always the phi plus. So the link layer of the client issues a single qubit gate to transform the psi plus to the phi plus state. And finally, the instruction layer issues a single qubit gate and a measurement to read out the output in a certain basis. And the physical layer report the real outcome. Okay, so the experimental results in this paper, to demonstrate and benchmark the capabilities of the link layer protocol, they execute on a 2-diamond and MB center-based quantum nodes 3 quantum networking applications: full quantum state tomography, characterization of entangled states of varying fidelity, and remote preparation of qubit states on the server by the client. So let's see each application. The first application consists on preparing entangled pairs and then measure them in different bases to learn the joint state. So they measure all 9 2-node correlators and their variations of 4,500 entangled pairs, and they use the software QPaper, which uses the Monte Carlo method to analyze the measurement outcomes and compute the fidelity, which is 0.793 with respect to the state phi plus. This is slightly lower of what they measure without the QGP in this paper. But one of the reasons for this discrepancy is that this QEGP, they implemented this QGP such that always delivers the phi plus. So if they create an state that is different, the link layer issues an extra single gate qubit to transform the state to the state phi plus. The second application is different because in the first one, I didn't say it, but they fix the target fidelity to one value. And here what they do is that they target 7 different fidelities and they measure the results, which are shown here. And we see that the measured and the targets are pretty close. So this is an important result because it means that the system can deliver entangled pairs with desired fidelity. But also, in addition, for each target fidelity, they measure the entanglement generation latency, which is defined as the time between the instruction to create entanglement is issued to the link layer until the successful outcome is reported by the physical layer. And we can see that the main contribution comes from the entanglement generation process in the physical layer, followed by the preparation of the MB center. But also what's important here is that the link layer, which is the orange one, always adds an average 10 milliseconds to the latency. This is due to synchronization, because if you remember, we want that both nodes trigger entanglement at the same time. So after attempting entanglement, they have to wait till the next time being to attempt again. So this adds a delay. But this problem is solved when multiple entangled pairs are requested. So each of the time slot is occupied by one instruction, and there is no such a delay. The final application is different, because here the client can measure its end of the entangled pair as soon as the entangled pair is created, but the server has to keep its qubit alive and wait for further instructions. This is a fundamental step towards the blind quantum computation, because the blind quantum computation, where the user can run applications in a remote server while keeping the computation private. They show this feature by the following process. They first establish entanglement between the client and the server. They produce an entangled pair. They measure the client's node, and they perform tomography in the qubit of the server to recover the state. They prepare the 6 cardinal states. Here are the results. You can see that they are not perfect, but they are quite good. The average fidelity is around 0.85, so it's quite good. In conclusion, what we can conclude is that the quantum link layer and physical layer work experimentally, but in order to scale quantum networks, we'll have to face a lot of different challenges. But what's the beauty of this paper, the one I mentioned multiple times, is that these protocols can be implemented in any quantum platform, in trapped ions, cold atoms, photons, superconducting qubits. And they are so simple, but at the same time they are very important to construct the basis and the grounds of a future quantum internet. Thank you very much.